So my name is Jon, for those of you who don't already know me from one medium or another. So one thing I keep observing about the Rust community is how we're all like allergic to unsafe code, or we think that unsafe code is just totally fine and nothing to worry about. And I wanted to take a little bit of time to talk about what unsafe is, because I think a lot of where the community's lack of alignment on this particular topic comes from a fact that unsafe is a bit of a mystery to many of us, and I think I want to solve that problem. I'm not of the illusion that I can solve this problem in like 25 minutes, but I will try. So in this talk, I'm going to try to demystify unsafe. I'm not going to teach you how to write correct unsafe code, but I am going to try to explain some of the reasons why you might actually want unsafe and some of the reasons why you should be careful about unsafe, and it's not something you should use just sort of willy-nilly. You could also sum up this talk basically as it's just C versus it's certain doom. Neither of these extremes are correct. And it's very important that we all agree on this. Like, writing unsafe is not just writing C code. It is more dangerous than that, and I'll explain how. But it is also not certain doom. There are a lot of things that unsafe is necessary for or useful for, and we need to acknowledge that as well. And so I want to go through first why we need unsafe. Like, why do we have unsafe in the language in the first place? Right? Rust is supposed to be a safe language. Why unsafe? And it turns out there are a bunch of reasons why you need unsafe. In particular, unsafe is there to ensure that we can write code whose safety relies on invariants that the compiler cannot check for us. And I'll go through some of these examples as we go through these slides. But the idea is that in unsafe code, we are the borrow checker, because the borrow checker cannot check whatever it is that we are doing. And not just borrow checker, but more about the sort of safety guarantees and requirements that Rust has. The first example of this is working with hardware devices. So when you work with hardware devices, and let's say you want to show something on the screen when your computer boots. At this time, like, there is no operating system. All you have are just like raw pointers that are specified in like the Intel manual or the BIOS manual or the manual of some obscure thing from the 80s. And so you happen to know by magic that at this address in memory, there's a chunk of bytes that you can write to and then text appears on screen. It's true. This is where you can write stuff to write things on screen during boot. The compiler has no way of knowing this. This is something you know as the programmer. And you know that no one else is writing to that address right now because you're in boot mode. Like, there is nothing else. There are no threads. And so you know a bunch of things that the compiler does not. So you can write this code, right? You can cast this pointer to a mutable pointer and then turn it into a mutable slice. You know that this code is safe. At this moment in time, the compiler has no way of knowing. Writing this code anywhere else, like in your regular like fn main, would not be safe. But it is safe during boot on hardware where you know this pointer is mapped. This is the kind of stuff we're dealing with where unsafe is necessary because the compiler has no hope of checking this code. Another example is when you want to interact with external code, right? Imagine you want to call into a C library, or maybe the C library is really like Java through JNI or something like that. The compiler has no idea what that code does. For all it knows, like, it's just going to write zeros to all of memory, right? It has no clue. You are asserting that you know that the code that this ultimately calls doesn't do something stupid. You're asserting that that code upholds all of Rust's safety guarantees. The compiler can't check it for you. It has no way to do that. And so you need to use unsafe to tell the compiler that you have checked. Another place where unsafe comes up a lot is when writing concurrency primitives, right? Imagine that you want to implement the mutex type. What does the mutex type do? Well, internally, it holds just a straight up pointer to some place in memory that sometimes it gives out a mutable reference to. The compiler has no way to know that we are carefully checking all of the invariants to ensure that we only ever give out a mutable reference to that pointer to one thread at a time, right? Like, this is the API for mutex, right? When you lock, it's going to do some kind of atomic. This is not how all mutexes are implemented, but this is one example where you're going to just like compare and swap a value until it becomes true. And at that point, you know that no one else is in this segment of code. No one else has a mutex guard. And so it is OK for you to implement deref mute for that guard and give out the mutable pointer. But the compiler can't know this. The compiler doesn't know that no one else is swapping this back to false, right? And so we need Unsafe to tell the compiler that we have carefully read our code and we know that is the case. There is another category that I'm hesitant to even raise, but I think it's an important one when we talk about Unsafe, and that is overcoming borrow checker limitations. There are some patterns that the Rust borrow checker is not quite smart enough to figure out yet. Usually these are already known issues, and you can look them up on like the Rust issue tracker. One example of this is if you want to return a reference early by downgrading a mutable reference. So this function right here, if you have this sequence of functions, this will not compile currently on the Rust compiler under the current borrow checker. It's a known bug, and it's something that you have no way of writing this code correctly that the borrow checker will accept. And so you can fix this with Unsafe. You probably shouldn't. Like, find a different way to write your code. That is probably better. And this is also why I'm not showing you the code to work around the borrow checker here, because you probably shouldn't do it. Generally, if the borrow checker tells you that your code is not safe, it's right. And if you get into the habit of like forcing it to just like, yeah, I know what I'm doing, you're probably wrong some of the time. And that can have really bad consequences, as we'll see later. Usually, with a borrow checker, it's better to either write your code slightly differently or just wait a bit. The borrow checker is improving day by day. We also have Polonius, this new sort of borrow checker iteration that's coming down the line, which will fix many of these problems. The last category that comes up a lot is performance optimizations. And this is maybe the most contentious way to use Unsafe, where there is a safe way to write your code, but you chose to write it in an unsafe way because you wanted like the very last ounce of performance out of your code. And sometimes that really is necessary. But I urge you to measure first, and preferably twice. It is very rarely worth that marginal performance increase that you usually get at the cost of what adding Unsafe to your code introduces. Because now suddenly you are telling the compiler that you have checked some invariant that you need to make sure holds for all eternity going forward in your code. It is much easier to just not have that responsibility. If you do measure and you find that it's necessary, then do it. Unsafe is there for that, but be very careful. Now that I've mentioned some of the reasons why you might need Unsafe, I also want to talk about the ways in which Unsafe can go wrong. Because this is where the sort of other extreme of the crowd often lands, is that we need Unsafe for a bunch of things, so we're just going to use it. What's the worst that could happen? Like, you dereference a pointer, you get a seg fault, ooh, that's not that bad, right? And it turns out that's not all that can happen. Bad Unsafe is a real problem. Remember that with Unsafe, we're telling the compiler that the code is okay. We are telling it that we checked it manually, very rigorously, that everything is right. We checked that the code never violates any part of Rust safety guarantees. That the Rust type systems guarantees are all completely in place. We're asserting that the unsafe code is safe. Unsafe is not a way to avoid the rules of Rust. It is an escape hatch that lets you write code with fewer restrictions, but you still need to uphold all of the Rust safety guarantees. And it all comes down to, are you sure that you're upholding all of Rust guarantees? Do you even know what all of them are? If the answer is no, then you should learn what they are, or you should not be writing unsafe code. Because some of them are pretty subtle. In particular, the compiler assumes that all code, whether safe or unsafe, always follows all of these rules and a couple of more. It assumes that no code ever dereferences a dangling or unaligned pointer. It assumes that no code ever violates the pointer aliasing rules. I should say reference aliasing rules, sorry. It assumes that no code ever causes any unsynchronized data race with the write. It assumes that no code ever produces an invalid value, and there are all sorts of invalid values. And there's a lot of debate, even among the people who really know Unsafe, as to what a valid value even is in Rust. Is any bit pattern a valid F64? It's not clear. Maybe. This is one of the things that they're trying to figure out. Is any bit pattern for a Boolean byte valid? It's not clear. I think the Rust spec currently says it has to be 0 or 1. Trying to take any other bit pattern and casting it to a Boolean is undefined behavior. And you need to be aware of all of these rules if you are to write correct unsafe code. Some of them may not apply, and in some cases, the ways in which bad unsafe code relate to these might be hard to discern, but it's worthwhile to keep in mind that these rules always apply to you. So what are the effects? Like if you break one of these, what happens? Well, usually incorrect use of unsafe is undefined behavior. Not always. There are some cases where it's not, but usually that is the case. And undefined behavior is like playing Russian roulette. Okay? I cannot say this strongly enough, that when you use unsafe code incorrectly and you end up with undefined behavior, you have no guarantees what your program is going to do. And the effect ranges from none to your program segfaulting to arbitrary data corruption in memory. And think about what that means. That could mean like your code takes an entirely different path through your program. The wrong data gets stored in your database. The access check gets flipped from a false to a true. You have no idea. Worse than that, when you have undefined behavior, the effects may not appear today, but then suddenly appear tomorrow. Even for no reason. Like it might depend on your hardware or the hardware the person is running it on. It might depend on the exact compiler version. It might depend on the phase of the moon. You do not know. And that is why you need to be so careful with undefined behavior, because it's very hard to predict where it's going to go. You basically have no guarantees. And in all code you write, you should avoid undefined behavior. Like it is just never okay. So let's look at some examples of things that can go wrong. So there's some code on the slides here. I want you to look on the left side first. So on the left side, I have a function compute, and it takes an immutable reference to a number and a mutable reference to a number. And if that number is greater than 10, then it sets the second number to be 1. If the input number is greater than 5, then it doubles the second number. In Rust, the compiler is allowed to assume that the code on the right is the same as the code on the left. That is, it's allowed to assume that it can just read the left value once and just sort of cache it. And they can optimize away the double check for the if. And specifically, in C and C++, this optimization would not be legal because I and O, the two parameters to the function, could point to the same memory. In C, that is totally the case. And if they point to the same memory, then imagine what happens. We take this branch, but then we don't take this branch. That is possible in C, that is not possible in Rust. And so if you break the aliasing rules, as an example, right? Imagine that you have some value and you give out a mutable reference and an immutable reference to it. Someone could call a function like this. The compiler optimizes it into this under the assumptions of the aliasing rules. So it runs it this way. So your code now suddenly produces the wrong answer because you were violating the aliasing rules which the compiler relied on. Another example, this is a bit more code, but I want to walk through it because it's a little bit subtle. So here we're going to write a function on vec that is going to be extend map. And the idea is it's going to take a slice of u's, and it's going to take a function that maps u's to t's, and then it's going to extend the vector with the mapping of each u to a t, right? It's a relatively straightforward function in terms of what it does. And we are smart developers. We don't want to do many pushes in a row because then we might have to grow the vector multiple times, and that's a waste. So what we're going to do is we're first going to reserve enough space in the vector for all of the elements we're about to push. And then we're going to get the current length, and then we're going to unsafely set the length of the vector and keep a pointer to the beginning of it. And then we're going to loop over all the inputs, call f on each one, and do just a pointer right into the next element in the vector. Now, this code is correct. Like, there's no bug in this code. There's no bug in the business logic of this code. If you run it and everything goes normally, then this executes correctly and does the right thing. So you don't need to look for that. But I want to ask you a question. What happens if f here panics? If f panics, then this function is going to return, and its parent is going to panic, and it's going to bubble up, and eventually this vector is going to be dropped. When this vector is dropped, what does the vector do? It walks all of its elements and calls drop on them. But we set the length here, and we panicked before we wrote out all of the elements. This means that some of the elements in the vector, so some of the things that are between the start of the vector and the end of the vector, contained uninitialized memory, right? We haven't written those values yet. And so dropping them is just going to call some arbitrary garbage memory, and this is undefined behavior. It turns out that this is one of the reasons why writing a correct drain implementations for data structures is really hard, because you need to deal with this problem of what if someone panics after they call drain? Or what if someone just doesn't call next all the way? And you need to think about all of these cases. Here's another one that I actually ran into relatively recently with a similar data structure. So here, we're going to have something called a lazy drop vec. And the idea is that we want to be performant. And so therefore, instead of just dropping every element when we drop a vector, we're just going to like push it to some global queue, and then we're going to drop them all later. And some unspecified time in the future, because dropping them in batch is probably more efficient than dropping them one by one. Right? So when it's dropped, we're going to walk all the elements of this vector, and we're just going to drop later into some like global collector. It's not important what it is. So this code is wrong. And the reason it is wrong is if this T is some type that is not static, that type contains a reference of some kind. Imagine it contains a mutable reference to a TCP stream. And when that type is dropped, it's going to write it to that TCP stream. Well, that mutable reference is no longer valid by the time this collector decides to drop things. And so here's an example of the bug is in the safe code. The bug is that T needs to require static here. Otherwise, this is not OK. When you have unsafe, the unsafety is not just about the code contained in the unsafe block. It's about the entire public visibility boundary of that code. You need to audit the safe and unsafe code in any module that contains unsafe. Here's another example that many of you might have heard of already. So this is the offset of macro. I've taken it from the mem offset crate. It's a little bit more complicated in the crate, but it's basically this code. OK, so here we construct some uninitialized memory, and we use the maybe unit type because we know that that's important to tell the compiler we're not going to use this memory because it's not initialized yet. We get a pointer to the start of the memory. We here get a reference to the given field of that initialized memory and just cast it to a pointer, right? And here, we're not even dereferencing the pointer, really. We're just taking an address, right? And then we compute the offset of the given field inside of that type as the difference between the two pointers. The problem here is imagine that this type is repr packed. So if it's repr packed, what that means is there's no space between the different fields. There's no padding in the struct. This means that types are not guaranteed to be aligned to their own size. So if you have a U64 normally in a struct in Rust, then it will be aligned to a 64-bit boundary. It will be 8-byte aligned. Similarly, a Boolean will be byte aligned, U16 will be 2 bytes aligned, etc. And Rust requires that every reference is aligned. It must refer to an aligned location for the type the reference is for. Right here, we are constructing a reference to a field. We're not dereferencing it, right? We're not reading or writing this memory. We're not using the pointer. We're just constructing a reference and then immediately casting it to a pointer. This is undefined behavior because you are constructing a reference that is not aligned or might not be aligned. And so if someone tried to call this with a type and a field and a packed struct, then they would be invoking undefined behavior in what appears to them as safe code. What the compiler does with it, it's hard to say. Who knows, right? But it's important to know that these things can be broken in this way. And so when it comes to the integrity of unsafe code, you have to remember that safe interfaces to unsafe code, they have to behave correctly no matter what the safe code does. When you write unsafe code, you can't rely on the safe code being correct. You can rely on the safe code being safe. you can rely on it not corrupting memory. But like if someone has like an eq that returns randomly true or false, or that like their order is random, or there's like a weird implementation of deref that like derefs to an arbitrary element of a vector or something, like your unsafe code needs to not have undefined behavior even in those cases. This is one thing that the standard library worked a lot with when it came to B-tree maps, is that the implementation of B-tree map has a bunch of unsafe code, but they can't rely on the ordering of the type being correct. They can crash, like crashing is fine, it's just you can't accidentally invoke undefined behavior, and that took a lot of thinking for a complex data structure. When it comes to sort of internal unsafe code, this is something that comes up a lot, especially when we look at other people's projects, is that they have unsafe code inside of their library, and they go, this unsafe code is fine, even though I haven't maybe audited it that much, because no one can get to it. No one can use it, no one can call it externally, and therefore it is fine. And that is not true. First of all, safe code in the same module as unsafe code, as we saw, can have an effect on the safety of the unsafe code. And part of the reason for this is that in safe code in the same module, you can access things like private fields. And the unsafe code might rely on the integrity of those fields, but it has no way to say so. And so the safe code might accidentally change that code. This is why encapsulation of unsafe has to happen at the visibility boundary, which is usually the module boundary, but think of it as it has to happen at the boundary where things are pub. And keep in mind that you don't generally want to assume that callers of your code are going to remember all the safety invariants. If you have some type that internally uses unsafe, but you make the function safe so that you don't have to put unsafe everywhere, then that's all good and well. But what if like 4 years later, you're modifying some code and you're calling that safe function, and you forgot that you can't do that if you also called some other function somewhere else, but it's not marked as unsafe, so you don't think twice about it. This is why even in your own code, try to make sure that anything that is unsafe is marked as such. Now, going through this, you might think that like all hope is lost, right? Like there are all these reasons why we need unsafe, but it's really hard to get unsafe code right, so we should just give up and go home and go back to UC or Java or something like that. And I would argue that's not the case. It is totally possible to write correct unsafe code. There's a very simple checklist. First of all, be sure that you need unsafe code. And second, be like really sure. And third, read the nomicon. So the nomicon is sort of like the Rust book, but for unsafe. It documents a lot of what I've talked about here and a lot more that you need to know in order to write correct unsafe code. Make sure you read it like preferably start to finish. And then just be very careful. Whenever you're writing unsafe code, keep this fact in mind. Whenever you write the unsafe keyword, you need to think about the implications of that and look at the other code in that same module. You also then want to make sure that you document all of your unsafe blocks. It does not just unsafe functions and such, but any unsafe block as well. Put a little comment above it with like safety : and then explain why that call is safe. It's going to save you a lot of trouble later on when 4 years later you need to figure out why this code is safe. Or if you get some contributor to your project who has to figure out whether this is actually safe because someone reported a bug. And then I recommend that you set up CI for your project to run Miri and the address sanitizer. These are both relatively straightforward to set up for Rust projects. I highly recommend both of them. I want to take a brief aside when it comes to Miri, because Miri is a fantastic tool. So Miri is a interpreter for Rust's Mir, like the mid-level interpreted language, or representation, I guess, that Rust has. And basically, it lets you run Rust code in the compiler. It lets you interpret Rust code while you're in the context of the compiler. And it does so essentially by emulating all of memory at compile time. And this means that it can check that your code doesn't do anything bad. It can run your code, run a test or something like that, and make sure that every reference that is constructed is aligned, and all of these other things we've talked about. And it even works on the playground. Like on the Rust playground, you can click a little button and then run Miri, and it will helpfully do things to your code. So for example, for the broken extend map we had earlier, I tried this code on the playground. So I created an empty vector, and then I tried to extend it with the map closure just panicking. I run it through Miri, and Miri says, not okay. Type validation failed. It encountered uninitialized byte, but it expected something that was not uninitialized, basically. And if you look back at the trace, you'll see that it ultimately ends up at vec drop. This is extremely useful if you're writing unsafe code to get this kind of information of, yes, your unsafe code is not correct. Here's how to fix it. So with that, I hope that you've understood a little bit more now about why we need unsafe and the ways in which unsafe is dangerous and what you can do in order to try to mitigate the risks of that unsafety in your code going forward. Thanks, and that's all I have. Question?
How does repr work at all if you're not allowed to take a reference to any internal field?
How does repr work at all? So for repr packed, you mean specifically?
Yes.
Yeah. So for repr packed, it used to be that the compiler would just let you take references to fields. It is now, after they realized that this was not okay, if you have a repr packed type and you try to take a reference to a field that happens to not be aligned, you'll get a compiler warning. And that is going to become a hard error, probably in the next edition. As far as to how you use them, this is one of the reasons why it's tricky to use packed structs in Rust at the moment. This is also one of the reasons why we have the an RFC that recently came up on raw pointers, on being able to take a raw reference, which is a reference that does not have the alignment requirement, basically. Yep.
So do you have an example of incorrect unsafe code that does not result in undefined behavior?
Incorrect unsafe code that does not lead to undefined behavior.
Because you left that open.
Not off the top of my head. I mean, obviously you can write unsafe code that just like adds two numbers incorrectly, right? Like it's incorrect, but it's not incorrect because it's unsafe. I can't immediately think of one, but the two categories are not entirely overlapping. I just can't think of one off the top of my head.
Wouldn't you just create a data race with
A
undefined?
data race between a write and a read that is not synchronized is undefined behavior. Question?
So this is kind of far out there, but in the Haskell space, we published a couple papers about trying to prove that traits are lawful, or type class instances are lawful, and obey the laws for OR or EQ that an implementation or a library could then use. If you have a verified OR instead of an OR, you can make that assumption in the data structure library. Is anybody working on some kind of formal method strategy like that for Rust? I know the Rust Belt project ultimately wants to help verify unsafe blocks, but that's a little bit different than just verifying the correctness properties of it.
Okay, so I'm going to repeat your question just for the recording. The question is, there have been a bunch of efforts on proving that certain traits are lawful in the sense that they follow their contract. This is things like ORD and EQ, that they actually do something sensible and correct. And the question is, if you have something like that, the first question is, if you have something like that, can you take advantage of that in your implementation? And the second of that is there such an effort for Rust? Yeah. So whether you can take advantage of that, probably. My guess is certainly in the B-tree map code, I'm sure there are cases where they have to do something a little janky because just in case the user did not use ORD correctly. I don't know of any particular optimizations you can make, but it might be able to remove some extra safety checking code. I'm not sure. As for efforts in Rust to do this, I don't know of any. There might be, but my guess is also that with something like Rust Belt Rust, you would sort of get this because once you prove the correctness of code according to some specification, then you already have pretty strong guarantees. Although that's more about safety. So what they could do then is they could show that if the ORD implementation was not sane, that the code still does not exhibit any undefined behavior. Great. Thank you, everyone.